Hello all, I am John Pinkham, a first-year graduate research assistant at the University of Maine. Today I'll be talking to you about my master's research. The focus and goal of my research is the development of live load distribution factors for composite tub girder bridges using finite element modeling. The composite tub girders were developed at the University of Maine and are made of fiber reinforced polymers, FRP, to offer a high strength material at a relatively low weight with non-corrosive material properties. Many bridges and roadways, particularly in Maine, experience exposures to harsh chemicals such as road salts, which contribute to corrosion. The development of bridges using non-corrosive structural members could lead to less maintenance and longer lifespans for the structures, therefore lowering the life cycle costs. With any new technology, there's unfamiliarity, and many like to stick with what they know. And in the current state of bridge design, that's steel and concrete. To help bring more familiarity to the composite tub girders and simplify the design process, a design guide is in development and will require live load distribution factors. The live load distribution factors will quantify the amount of load applied to a single girder so it can be designed as a single beam. Both shear and moment will need to be quantified. The current design practice is to use the live load distribution factors in AASHTO for a Type C concrete box girder bridge. The first bridge to be constructed using the composite tub girders was in Hamden, Maine, and will be referred to as Hamden-Gristmill Bridge. Hamden-Gristmill Bridge has been live load tested twice since its construction finished in December of 2020. During both tests, longitudinal strains were measured, and using those results, distribution factors for moment were inferred and can be seen in Table 1 in the lower left corner. Table 1 compares the distribution factors inferred from the load case of 2 lanes of trucks during testing and those calculated using AASHTO equations. As can be seen, the AASHTO equations do not match well with the inferred distribution factors from the test. A maximum difference of 90% is visible in girder 1, which is the exterior girder under the sidewalk. And then the interior girder's maximum distribution factor has an increase of 3% from that of AASHTO. This shows how important it is to perform the research to quantify distribution factors that are applicable to the composite tub girders. Table 1 only compares moment distribution factors. However, shear distribution factors are also important, and with 2 webs within each girder, quantifying the amount of shear within each web is important for design. It could be assumed that the shear on one girder is evenly distributed between webs. However, figure 1 in the center shows the shear strains in each web are not the same, where there's nearly a 50 microstrain difference, which represents a 20% increase in the amount of shear from one web to another within a single girder. Moving forward, the research approach can be laid out in 5 steps. Step 1, live load test 2 Hamden bridges, Hamden-Gristmill, and then a second that is nearing completion, also in Hamden. Step 2 is create FE models, finite element models of both Hamden bridges. And then step 3 would be calibrate these FE models in step 2 to the test results from step 1 to verify FE analysis as a viable practice for quantifying the composite tub girder behavior, and then therefore using it to develop the live load distribution factors. Step 4 is create a suite of the finite element models to use in a parametric study where the models are simulated under many load cases to maximize moment and shear within each girder. And then step 5 would be using the results from step 4 to develop equations that give the distribution factors for both moment and shear for both interior and exterior girders based on the parameters looked at in the parametric study. The parameters that are proposed to be included in the study are span length, girder spacing, skew angle, number of girders, overhang, and deck thickness. Girder spacing will be of important significance as it is a typically a parameter that has the most effect and will be looked at widely. These parameters and their proposed ranges of applicability will account for 3,330 different models, which is subject to change and be reduced to a more feasible number as these models will take a bit of time to look at and therefore 3,330 models might not be all that feasible. Each model will have a girder cross-section designed for using the design guidelines that are in the development stage and based on previous research. This way, the study will use a reasonable girder cross-section for the bridge dimensions. Therefore, it's not too small and will have premature failures in the model runs, or it's too large and draws more load to a stiffer element than need be and creates unrealistic results. Under the current status of the research, in July of 2022, Hampton Gristmill Bridge had a second live load test completed. A key addition to this test compared to the test in 2020 was the implementation of strain rosettes that quantified the shear strains in each girder web. An example of one of those strains rosettes can be seen in the top right image. The test data was processed and compared to calibrated FE model that is also shown in the bottom right image. Figure 1 showed the differential shear observed, which was also noticed in the finite element results. So we know that finite element results proved to compare well once calibrated. And then the differential shear will be examined in the parametric study mentioned in step 4 of the FE models to account and will be accounted for in the shear distribution factors if need be. Progress has also been made in the research approach step 4 to create a suite of FE models. This is still in the developmental and proof of concept stage and is looking good. I'd like to thank all those who have helped in the research so far, including the Maine Department of Transportation, AIT Bridges, my colleagues, Andrew Skank, Keith Barabee, Jake Bear, and my advisor, Bill Davids, as well as TIDC and UTC programs for giving me the ability to perform this research. Hope you all have a good day.